Okay, we're going to look at the domain of a logarithmic function. So I'm going to recall for you y equals log base 2 of x and show you what this graph looks like. First of all, the graph has a vertical asymptote at x equals 0. Then where our x values are positive, we're going to have outputs for y that go from negative infinity on the y-axis to positive infinity on the y-axis. Negative infinity because this graph will go down towards negative infinity, and positive infinity because as we make this turn, it's going up and right, up and right, up and right. So it will go up forever and right forever. So the domain for this function is x is greater than 0. In interval notation, we're used to writing that 0 to infinity. So this would be the domain for this function. And you can clearly see that our graph will never allow for x to equal 0, and it only includes positive values of x. Now, this part right here is called the argument. So I'm going to refer to this as the argument. So the argument must be greater than 0. Now let's try this without a graph, just looking at the equation. So here's an equation or a function, y equals natural log of x minus 4. What we're going to do is we're going to look at this argument and we're going to make sure that it stays greater than 0. So I'm going to take x minus 4 and I'm going to create an inequality. X minus 4 is greater than 0. I solve that inequality and I get x is greater than 4. On a number line, x is greater than 4 would look like this. Therefore, we'd have 4 to infinity as our domain. Now, in previous classes, you would have learned when the argument is quadratic, it's not as simple to set that inequality greater than 0 and solve. So let's try one of these. When I'm looking for the domain of logarithm, I'm going to set the argument greater than or equal, not greater than or equal to, just greater than 0. Now, in order to solve this inequality, this is a parabola that opens up. So what I want to do is I just want to show you just a little sketch of what this might look like. This parabola is going to look something like this. Now, not exactly, but it's going to look something like that. And we want to know where the actual parabola is greater than 0. Well, the parabola would be greater than 0. This is your 0 right here. So this is 0. Your parabola would be greater than 0 when the parabola is above the x-axis. So that interval would be from negative infinity to this number, and then from this number to positive infinity. Because if I put negative infinity or negative 100 or negative 10 into the inequality, my output is going to be positive. If I put negative 5 into my quadratic, into the inequality, my output will be greater than 0. If I put a 0 into the quadratic, 0, 0, minus 4 is negative 4, my output would be negative. Now, negative outputs are not going to satisfy this inequality. This inequality says we want positive outputs. Positive outputs. So we're going to use a form of factoring to help us find where these key points are. So I'm going to call them key points. And I'll show you what I'm talking about. This right here and this right here are our key points. So let's see. We've got x squared plus 3x minus 4 is greater than 0. I'm going to factor that, and I'm going to get x plus 4 times x minus 1 is greater than 0. Now the key points are going to be negative 4 and positive 1. I use the zero product property to give me the key points. However, this is an inequality. An inequality cannot get its answers using the zero product property. The zero product property says if you multiply two numbers and one of them is 0, then their product will be 0. We don't want the product to equal 0. We want something that's greater than 0. So we're just going to use these key points, negative 4 and positive 1, and then we're going to look for the truth in each one of these intervals. We know we have from negative infinity to positive infinity, and we possibly have a break somewhere in between or maybe on the ends. So I'm going to pick a number between negative infinity and negative 4. I'm going to choose negative 10. If I put a negative 10 in to the inequality, I would get negative 6 times negative 11 is positive 66. So these would give me positive outputs. Positive outputs. If I try between negative 4 and 0, negative 4 and 1, I'll put a 0 in. I would end up with 0 plus 4 is 4. 0 minus 1 is negative 1. That would be negative outputs. Negative 4 is not greater than 0. Then if I try over here on the last interval, if I put a 10 in, I would get a 14 times a 9. 14 times 9 is a positive output. I need positive outputs because I want greater than 0. Greater than 0 means we want positive outputs. Therefore, my interval would go from negative infinity to negative 4, union with 1 to infinity. These would be open intervals, meaning parentheses, because I do not want equal to 0. I only want greater than 0. And if I put a negative 4 in, I'm going to get equal to 0. If I put a 1 in, I'm going to get equal to 0. I don't want equal to 0. I just wanted greater than 0. Therefore, we have parentheses. And I think that about does it for domains of logarithmic functions.